The squeeze theorem is really very useful at times when we could otherwise not be able to compute limits. And the idea is that we squeeze one function between two other functions. Sometimes this is called the sandwich theorem. And you can think of the outer functions as the pieces of bread and the inner function as whatever's the peanut butter on the inside. So we say if f of x is less than or equal to g of x is less than or equal to h of x for x near a. This is where we're going to be interested in the limiting point. And if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x is equal to some number L, then the limit as x approaches a of the piece in the middle is also equal to L. And so the idea here is that we have some value L here on the vertical axis, and we have this point A here on the horizontal axis, and we have a function which is the top of the sandwich that looks like that, and a function that is the bottom of the sandwich that looks like that. And then we're interested in our function g, which is in the middle, which could be doing any kind of thing. So this is g in the middle, and we have h on the top and f on the bottom. And so the idea is if both h and f come together at a point in the middle, then g has to be sandwiched in between h and f, and it has to attain the same value. And so this is actually quite useful for things like the following. Consider the limit as x approaches 0 of x squared into 1 minus cosine 1 over x. Okay, so to start with, you could say, well, if I'm going to compute a limit, why don't I just plug in x is equal to 0, and we'll get a 0 for x squared. But then 1 over 0 is not defined, and so we can't evaluate the cosine function. In reality, this function looks something like this. And so this vertical axis is going to be x squared 1 minus cosine 1 over x, and the horizontal axis is x. And so we'd like to be able to compute this limit. And so what we need to do is to find an f and an h. So let's write the function over on this side. We have x squared 1 minus cosine 1 over x. And so we need to deal with the cosine function. And we know that cosine 1 over x is going to lie between 1 and minus 1. And so if we multiply through by minus 1, we have 1 is greater than or equal to minus cosine 1 over x is greater than or equal to minus 1. Now we'd like to add 1 to this inequality. So we have 1 plus 1, which is equal to 2, is greater than or equal to 1 minus cosine 1 over x is greater than or equal to minus 1 plus 1. And so this is 2 here, and this is 0. So 1 minus cosine 1 over x lies between 2 on the upper end and 0 on the lower end. So this tells us that the upper bound is by replacing 1 minus the cosine 1 over x by 2, and the lower bound is replacing 1 minus cosine 1 over x by 0. Recall our upper bound is h, and so we have h of x is equal to x squared times 2, and f of x is x squared times 0, which is equal to 0. And so we have our problem set up. Now we want to check to see if we can find this limit L. So the limit as x approaches a, which is 0, of f of x is equal to the limit as x approaches 0 of 0, which is equal to 0. That part was easy. The limit as x approaches 0 of h of x is equal to the limit as x approaches 0 of x squared. And this will also equal 0. So these are the values for L. And so together, this says that the limit as x approaches 0 of g of x is equal to 0.